Hello, welcome along. It is the Fun Kids Science Weekly. My name's Dan. It's our second chemistry special this week. And in this one, we're having a proper good look at the periodic table, discovering all the secrets that are inside and why it's laid out the way that it is. We'll chat to some science experts about some of the astonishing elements, about their favourite elements, why they're their favourite elements. We'll also have a look at a new sun cream that's been discovered in plants. We'll learn about how chemistry helps some chefs become like real life Willy Wonkers. That's a brilliant story. It's on the way a little later. And I've got some of your questions to answer. Today they're all about breathing and beavers. That's on the way after we catch up with Kareena's chemistry. We'll have a few episodes of these popping up this week. And here's the first.
Kareena's chemistry, with support from the Royal Society of Chemistry.
Bad news. My best friend Em is moving to Southend. I'm going to miss her so much. Chemistry showed up, but I wasn't in the mood.
Hiya! Hey, why are you so sad?
Look, it's nice to see you, but I'm not sure a chemistry superhero alter ego is going to cheer me up today. My best friend's moving. I just wish things could stay the same.
Where's the fun in things staying the same? Who's that kid in your class? You know, the boy with the orange glasses.
Super cool Luke, the scooter dude.
Yes, him. He changes his haircut every term, doesn't he?
Isn't it kind of cool to see what's going to come next? Well, yes.
And when you get down to it in chemistry, you'll see that most things change one way or another. Come on, I'll show you. It might cheer you up.
Well, it can't make me feel any worse. Come on then.
So everything in the universe is in one of 4 different states of matter: solid, liquid, gas and plasma. But just because they start in a certain state doesn't mean they'll stay in it. Watch out! There's some plasma. Duck! Phew! You get a lot of plasma in space, but you'll probably know the other 3 states of matter better. Let's start with a solid. An ice cube, in fact.
An ice cube? And you said these changes were exciting.
The state of matter affects substances in amazing ways, like how dense it is, how well it flows, how bendy it is, conductivity, in fact, all sorts. Anyway, I'll show you what I mean. Here we are. We're on the ice cube's surface. It's solid, right? Can you remember the atoms we saw the other day?
Yeah, they were well cute. Like little planets with the electrons going round like moons.
Well, let's see what they're up to in here.
Oh, it's pretty quiet and still in here, and it's crowded too with all these molecules joined together. I'm actually getting a bit squashed.
As you can see in solids, the atoms are really packed together. This packing or cohesion is made by special bonds, and it means that they can be pushed about without changing shape.
That's very nice, but I really am squashed in here. So we're all solids so stiff.
It depends how the atoms are joined up. If they're in stretchy string, like in elastic bands, then they'll be a bit more bendy, while atoms in things like metals and diamonds are meshed together more tightly, so they're much stronger and don't bend much at all. Fancy a change? Let's heat things up.
Oh, that's a bit better. The molecules are moving a little bit more. They aren't packed together so much, and there's a bit more room. Phew.
The solid ice cube is changing to a liquid. Any idea which liquid?
Water, obviously. I do know some things.
Just testing. When you add energy to a solid, like when it's heated up enough, it turns into a liquid. As a liquid, molecules are attracted to other molecules just enough to keep them in contact, but not enough to make them fixed in a shape. The molecules can continually move, which means that liquids can flow smoothly, which helps when you want to pour them into a glass.
Yeah, when you put solid ice in a glass, it sort of stacks up, doesn't it? But water fills it up and takes on the shape of the glass.
Whee! I like liquids. I'm going to slide down between the gaps in the molecules. Whee! There's one last change to show you. For that, we have to add even more energy. And that means turning the temperature up or the pressure down. And you might want to put this crash helmet on. Pressure keeps things under control, and the less there is, well, you'll see.
Crash helmet? Okay, nice helmet, cool stars. But why do I need a crash helmet? Ow! What's that? The atoms are going crazy.
This is a gas. And water as a gas is called water vapour, although you probably think of it as steam. Ow! You've got it! You wouldn't be able to see water vapour, but steam contains water droplets too, which is how you can see it when it's coming out of a kettle. In a gas, the chemical bonds are not strong enough to hold atoms or molecules together, so the molecules fly about colliding every now and then. That's why we need the crash helmets. Gases aren't as dense as liquids, although they've got something in common, as they tend to fill up the containers they're in, a bit like air does in a balloon.
Ouch! Okay, I think I get it.
And there's one more state that we haven't explored, and that's plasma.
Like in lightning. I don't think I want to get too close to that.
Yeah, plasma tends to be a bit like a hot soup of electrons flying around even faster. So I think we'll head back to your bedroom, where it's a bit safer.
Aw, and that's Dad. I've got to go. Well, I can see that things changing can be exciting, even if it is just an ice cube to start with.
And maybe your friend moving away will mean some cool changes for you. You never know. She might invite you to a beach party or something.
That would be good. Bye for now, Chemistry.
Kareena's Chemistry, with support from the Royal Society of Chemistry. Find out more at funkidslive.com.
Right, let's get some of your questions answered on the show now. Remember, if you've got something sciencey that you want figured out, something that you just can't wriggle out the answer to in your brain, let me know about it. I'll do all the research for you. You can tell me by leaving as a review for the Science Weekly over on the Apple Podcast Store. This is from Arlo, who is in Hertfordshire in the UK. Arlo asks, why do we breathe? Well, breathing is the action of taking oxygen into the lungs and then getting carbon dioxide out. You suck air in, and then the oxygen gets from the lungs in all the little sacs you've got in there. There's so many of them, which means they've got a greater surface area, so you've got a brilliant chance of getting that oxygen into the blood. It then travels through every cell in your body, pretty much, and it gives energy so that you can live. Now, the part of the brain that controls the breathing is called the medulla, and it's told by your nerves that there is too much carbon dioxide in your body, the levels of CO2 are too high, and that you need to get rid of it to take in some oxygen so you can get the energy, so you can live. It then forces your lungs to breathe out. And that means you have to breathe in. That's just the way lungs work. So it's not just your need to get oxygen into your blood that's why you breathe. It's quite a lot of it is the fact you need to get carbon dioxide out of there. Thank you so much, Arlo. Right, this is from Ryan, who's in Wales. Ryan asks, why do beavers build dams? Well, beavers build dams to have a home. They make a pond of deep, quiet water in the river so they can chill out, so they can sleep at night, so they've got somewhere to live, and they can't have loads of river water going in there, so they blockade it with sticks and mud. They make the wall in the river. It slows down the flow so their home doesn't wash away. And actually, beaver dams are good and also bad for the environment. You see, it acts as a filter to keep bad sediment and toxins moving down the river and out into the ocean. But also, the build-up and the block that they use to make their dam can cause pretty disastrous flooding. So both good and bad there. Thank you so much, Ryan. If you've got a question that you want answered on the show, you need to leave it for me as a review over on the Apple Podcast Store. It's the Fun Kids Science Weekly. It's a chemistry special because it's the International Year of the Periodic Table. It's like a really important and useful chart. There's probably one in your school. All scientists use it. And it's all the elements that we know about. They're all laid in a very specific system. So to tell us more about the periodic table, we've got science journalist Izzie Clarke on the phone. Hey, Izzie.
Hiya, how's it going?
Yeah, thank you so much for joining us. I think we'll start with the periodic table. What's it all about?
So you might know that everything is made up of atoms. They're like teeny tiny building blocks that make up absolutely all matter in the universe.
I think I've got that. So everything that we see around us is made of atoms. Does that mean atoms are different to elements?
Yes, they are. So a chemical element is a substance that only contains one type of atom. So each element is different. Some elements you might know are silver, iron, gold, or calcium. And the periodic table of chemical elements is mega helpful because it just charts all the chemical elements that we know about.
Whenever I've seen a periodic table, it always baffles me. It's laid out in a way that doesn't seem to have any order. It looks completely random. I'm sure scientists kind of know what they're doing. Who actually decides which element goes where?
Right, so you might like sorting your Lego bricks, for example. Maybe that's by colour, all the red ones together perhaps, or maybe by shape or the job they do. And the periodic table is a way of doing pretty much the same thing, sorting the elements that we know about into a useful order. Chemists have been trying to sort elements for hundreds of years, especially as new ones were discovered. The chemicals in the periodic table today are placed in an order of something called their atomic number, which starts at the lowest number of 1, which belongs to hydrogen, and then they work their way up.
You can't just kind of chuck that in there without me following up. So 1 is hydrogen, then you've got this atomic number. What does that mean? What's an atomic number? It all sounds kind of hard.
It's actually really simple. So the atomic number of an element is the same as the number of these teeny tiny positively charged particles at the centre of an atom. They're otherwise known as protons. So hydrogen has 1 proton at its centre, so therefore its atomic number is 1.
So then we work up. So if you've got 2 protons in the centre, that'll have the atomic number 2, and it keeps getting bigger. It must get quite bigger, though. How many elements do we actually know about?
So this is the most amazing thing. Even though the universe is so incredibly big, there are actually only 118 elements that we know of, which is pretty incredible when you think about it. It's like there's just 118 different shaped Lego bricks, and from that set of bricks you can build a planet, a horse, a potato or a mountain range, literally anything that you can think of.
A potato or a mountain range. It's amazing to think, isn't it, that these two wildly different things are all made with the building blocks, and there's only, at the moment, we know of 118 different things that these can be made from. I mean, who came up with the idea of the periodic table anyway?
So over the years, different scientists have come up with ways to sort the elements. But the periodic table that we use today was the work of a scientist called Dmitri Mendeleev in 1869. The really clever thing about this is that by using the table, Mendeleev and others were able to accurately predict the properties of many elements before they were even discovered. It's a bit like if you're doing a jigsaw and the pieces are already in place and they can help you figure out the shape of that last missing piece.
Here's something for you. So Dmitri Mendeleev, he's got an element named after him. Atomic number 101 is Mendeleevium. So there we go. It all kind of nicely wraps up. I've been asking everyone that's joined us on the show, Izzie, what their favourite element is. What's yours?
It's a tricky one. I'm going to go with carbon because it is so useful. It's in literally everything and it comes in so many different forms. You've got pencil lead, diamonds, you can tear it down to tiny amounts and it's got really helpful electronic properties. But can I squeeze one more in? Because I would like to mention gallium. It's kind of helpful for electronics, but I mostly like it because it can safely melt in your hands and you get these really cool silvery droplets and they go everywhere. It's really weird and I love it.
It safely melts in your hands?
Yeah, it looks like a silvery water that sort of moves around. I would recommend going to look up a video of it because it's just bizarre.
Well, there you go. You need to go and find out more about gallium. Izzie, thank you so much for telling us all about the periodic table on this week's Science Weekly.
Thanks, Dan.
So today's chemistry special on the show is all about the elements and the periodic table. So I thought we'd have a quick look at the periodic table and run through some of the elements that are amazing and strange and a couple that we see and meet every day. Arsenic. Let's talk about arsenic. We've spoken about it before in our Dangerous Dan. It's element number 33. It's a poison. It used to be used in paints in the past before they realised how dangerous it was. Also, there's calcium. Calcium is number 20. It's a mineral. It helps make bones and teeth get stronger. Carbon. Carbon is a simple element. It's number 6. Almost all the life on Earth is based in carbon. Much of it was made at the Big Bang. Also nitrogen. Nitrogen is number 7, one up from carbon. Most of the air that we breathe in is nitrogen. Something like 70% of the air is nitrogen, and we don't really have much of a use of it. It shows how inefficient our breathing is. Also lead. Lead is number 82. It's the heaviest of all the metals. Mercury is number 80. It's used in some thermometers because it expands quickly and predictably in heat. You've also got hydrogen. Hydrogen is number 1, the simplest of all the elements. It's a gas. It's the most common element in the universe. There's chlorine as well. You know chlorine because it's used to keep swimming pools clean. It's element number 17. And finally, in this rundown, one of my favourites, iron. Iron, big and strong. It's number 26. It's been used for thousands of years to build pretty much everything. It's a chemistry special of our Fun Kids Science Weekly this week. So I thought we'd go back to basics to find out what really the whole fuss about chemistry is. So on the phone we've got Dr Joanna Buckley. She's from the University of Sheffield and the Royal Society of Chemistry. And she's going to tell us loads about the whole thing. Hey Joanna.
Hello there.
Thank you so much for joining us. I thought I'd start off. What sort of things do chemists actually do?
Oh, okay. So chemists, in a nutshell, I always think of chemistry. If we step back and think about what chemistry is, I always answer it's the science of stuff, as I think that just about sums it up. It's the science of matter and its properties. And what I love about it is it's called the central science for a good reason, because it connects and contributes to other aspects of life sciences such as biology and physical sciences such as physics. And I think knowing about chemistry allows you to understand other aspects of science better. And chemists, we carry out a whole range of experiments, but ultimately it boils down to creating and analysing new substances, both hands-on in a laboratory and via computer models. And we work towards certain goals, so whether that be to synthesize a new chemical compound for a specific application. For example, it could be a new chemical that goes into your smartphone to help your smartphone work better, or it might be to tweak the chemistry of an already existing compound. So there might be a drug, for example, and we're trying to optimize its properties. So we're problem solvers, and we do that in the lab and via computer modeling.
You say you do it in the lab and you're looking down all the chemicals that you're studying. How closely are you able to see these particles down to their most basic form? Can you actually see atoms and electrons and everything spinning around it?
So we can't see anything that small. In order to be able to analyse things on that scale, we'd have to use different analytical equipment. So once you've synthesised a chemical, you might already know what that chemical is, but it's really good practice to analyse it via a number of different chemical techniques so that you're pretty sure or almost certain that you've got what you wanted to achieve. So as I say, it could be in a lab, it could be via a computer model. Chemists can do their chemistry absolutely everywhere. I know some chemists whose labs are spread all over the world. So it could be in a mobile lab sampling ice core samples from the North Pole, for example, or it could be in an aeroplane collecting air samples from remote locations. Chemists can do their chemistry absolutely everywhere.
If you go back to the original chemists, like say 100 or so years ago, or maybe longer, when we were starting to figure out if you put that you can put two atoms together and then things keep growing, so you've got CO2 instead of just carbon and oxygen. How did they figure that out, and how did they then test it to make sure that they were right?
I think a lot of it back then was probably trial and error, because all of the techniques, all of the reactions that they were doing back then had never been done before. So a lot of it was, let's put these things together, let's heat this up to a certain temperature, let's see what happens. How they analysed that was a bit less sophisticated than what we do now, simply because the techniques available to them weren't as sophisticated as the techniques available to us now. But they would make the best of what they've got, essentially. And actually, we're learning even now. So back when Dmitry Mendeleev assembled the periodic table, and so other chemists were synthesizing different elements, they might get it wrong. They might synthesize the wrong element and call it something different. So it's interesting from a historical point of view to look back and learn from the mistakes of the chemists of yesteryear.
We've looked at history. What about the future of chemistry, Joanna? How much scope is there for us to keep discovering new elements, new substances, new way of doing things?
I think as a chemist, I think it's really exciting to look towards the future, look into the future. Whilst you might think the periodic table is finished and done and there's probably going to be nothing else added to it, there could well be more things added to it. It could well be more elements added towards the end. And how those elements, how those compounds interact and how we start to make new compounds, there's just so much scope. As I say, we can either start from scratch and make a whole new compound for a specific application, or there could be something that we could think that we could somehow make it better. And there are chemists doing both. There are chemists doing kind of blue sky research where they have an endpoint, but there's no there's nothing that's gone before, so they can't necessarily work on somebody. They can't look at somebody else's work and think they're going to improve it. So I think the future of chemistry is just as exciting as the past.
You mentioned heating up elements back then. It brings to mind how we are chemists every single day. I mean, you're in a lab doing your chemistry. How are us mere mortals? How does chemistry impact our lives?
So everything we interact with every day involves chemistry. And I think even now that still absolutely blows my mind. And you may think back to the day that first got you interested in chemistry. For me, I had a chemistry set when I was 7 and it absolutely blew my mind, I think, even, back then. But we do chemistry every single day. So a really good example of that is cooking. When we're cooking, we're absolutely doing chemistry. And what's really exciting is that's the chemistry that's personal to you. So I really enjoy food chemistry. It's an area of chemistry that I've kind of meandered into along the way. I first became interested in it when a batch of fudge that I'd made tasted absolutely awful, and I just couldn't put my finger on why. So I started applying my background in chemistry to the problem, and I quickly realised that I could become a much better cook by knowing a little bit more about what I was cooking with. So we do chemistry. We all do chemistry on a daily basis.
Now, let me ask you a question. Or you mentioned fudge then, and so I want to ask you about baking, because I know that baking is a way that we do cook quite often. It's a way that we're, using chemistry, we're changing one thing into another. But what about this? Why can ice cubes melt and then be refrozen? When you've baked a cake, you can't unbake it. You can't take it back to the ingredients.
Well, that is a great question. It's all to do with the type of change that's happening. So there are two types of change. There's physical changes and chemical changes. So in a physical change, no new compounds are produced, but it's just a structure that's changed. So we call that a reversible reaction because you can reverse it. So ice cubes, for example, are just frozen liquid water. Still the same, but it's just in a different shape or form. A chemical change produces new substances, and that's an example of an irreversible reaction, so you can't go back, basically. So in terms of cooking, you can get both chemical and physical changes that occur. So as you say, when you bake a cake, you can't recover all those individual ingredients back out of it because they've already reacted to form other compounds. So as I say, that's an irreversible reaction. However, when you do something like melting chocolate, you can cool it down again to form a bar. So that's an example of a reversible reaction. So in cooking, we do both types of reactions.
Right, let me ask you one last question about an element that I'm told that you know quite a lot about, silver.
I do. I love silver. I'm a massive periodic table geek. I think there are so many fascinating facts about the elements, these tiny little building blocks of everything in nature. And I believe everyone should have a favourite element and a reason why it's your favourite element. And when I talk to people about the periodic table, I always encourage them to go and look at how it's put together and what elements are where and what's next door to what, how they got their names, and what amazing chemistry they're involved with.
Well, can you tell us why silver is one of your favourite elements then?
Okay, so silver's my favourite. because, well, I spent 4 years of my life researching it, number one. But the main reason I love silver so much is because it's beautiful and it can save your life. And I think those two facts together are pretty awesome. So it's beautiful because it can be turned into jewellery and decorative items. And it can save your life because it can kill bacteria. And it's used in dressings to treat cuts and wounds. So thousands of years ago, the Phoenicians, Egyptians, Greeks and Romans first discovered that certain metals could reduce bacterial growth. This was long before we knew that microbes were hazardous to human health. And they used vessels, they used containers made from, particularly from silver, and they found that this kept their food and drink bacteria-free for longer. And the same chemistry is used today. So silver wound dressings, they look a bit like high-tech plasters. They can help to minimise bacterial infections on your skin by destroying these microbes that can be fatal. So that's why I love silver so much. What's really interesting is, as chemists, we're still not really sure how silver kills bacteria. And it's one of the questions people ask me a lot of when they know that I know about silver and they know I know about silver killing bacteria. They'll often say, how does it do this? And we kind of scratch our heads a little bit. We've got various ideas, sort of educated guesses, really good educated guesses, but nobody really knows. And I think that's interesting. The fact that we've known about it for thousands of years and still can't quite pinpoint the reason why silver kills bacteria is amazing. And it's actually, even now, it's a multi-million-pound industry. So even if you've never come into contact with a silver wound dressing, you might have seen it in supermarkets and in shops, because you can buy silver-containing socks that are meant to stop you from getting smelly feet. You can buy silver-containing deodorant for the same reason, pajamas and plasters and household sprays and water filters, basically anything you can imagine which would benefit from a more sterile environment. So that's why I love silver, because it is beautiful and it saves your life.
Amazing. Dr Joanna Buckley, thank you so much for telling us all about chemistry on this week's Science Weekly.
Thank you.
This week's Science in the News, it's all about some of the amazing discoveries we're still making thanks to chemistry. Like this, a molecule that protects plants from overexposure to sunlight might form the basis of a brand new sunscreen, or sun cream, or sunblock, whatever you call it. Research on the green molecule by chemists has found that it absorbs UV light and then disperses it. When they see it through the microscope, it looks a bit like it's doing a dance, like the light is doing a can-can, and this makes it an ideal filter to protect your skin. Also, polymer scientists in America have created liquid droplets which behave like tiny bar magnets. It's thought they could use these to deliver medicines right into the cells by attracting things towards the places that scientists need the drugs to go. And finally, molecular gastronomy is taking the world by storm as chefs use chemistry to become kind of like a Willy Wonka. It creates new flavour combinations and new textures. Using chemistry, they found out that freezing things at low temperatures changes the molecules inside the food, which is why now you can get bacon-flavoured ice cream, pork-flavoured cake, and loads more stuff. It's our chemistry special in the Fun Kids Science Weekly. On the line now to tell us loads more about elements and her faves. We've got Elisabeth Ratcliffe from the Royal Society of Chemistry. Hey, Elisabeth.
Hi, Dan.
Thank you so much for joining us. Now, we're talking about elements and the Royal Society of Chemistry. You must know loads about them over there. Why are elements so special?
Yes, so at the Royal Society of Chemistry, we love elements, and this year is the International Year of the Periodic Table, which is a time when we're celebrating this diagram called the periodic table that contains all the elements in the universe. So the reason they're special is that everything that you see around you is made of elements. So when you look at the periodic table, everything in the known universe is made out of these elements that are written down there. And most of them are naturally occurring, which means we can't make them. Scientists can't make them. They were created in stars before the Earth began. And most of the time, in order to get them, we have to dig them out of the ground. We have to mine them. And each of them have special individual uses. Nothing can do what each of these particular elements can do. So we have to celebrate these elements and get excited about them because each of them has a really unique job.
What qualifies something to be an element?
So an element is basically, if you think about an atom. So an atom is one of the smallest units of matter. There are things smaller than an atom, like an electron, a proton, and a neutron. But an atom is a single unit of matter, and those go together to make molecules, which go together to make compounds, which make the things that we see around us. So there are different types of atoms, and those are called elements. And what makes them different is how many electrons and protons and neutrons make up that atom. So a hydrogen atom has one proton and one electron, and then the next element along the periodic table has two protons and two neutrons and two electrons, and you go up through the periodic table like that, adding electrons and neutrons and protons. And those numbers make the atoms different from each other, and it means that they behave completely differently.
Is that the only way that one element is different from another? Fundamentally, at the most basic level, it's simply the amount of protons and neutrons, and that can change something from being a gas to being a metal.
Yes, that's exactly right. That's the only difference that there is. And it, as you say, it changes the difference between their states. So if they're gas or solid or liquid, it also relates to whether they're a metal or a non-metal. It also relates to their color, how they look, whether they're shiny or not, whether they conduct electricity, whether they're hard or soft, and also how they react with other atoms and other elements. So different elements will form different molecules with other different elements, and they go together in different ways, kind of like Lego bricks go together in different ways. So not all elements will go together with other elements. So it all depends on their unique properties.
And how many do we know of?
So there are 118 that have been discovered so far. So the first 90 are the naturally occurring ones, and then the ones after that had to be made by scientists in a lab. So the higher order elements, the ones with lots and lots of protons and neutrons and electrons, they're not very stable. So they usually decay soon after they've been created. So they break down. Basically, they lose some of their electrons and some of their neutrons, and they'll decay to smaller elements. So the biggest ones, number 118, which was only discovered a couple of years ago, it only lasts for fractions of a second. So it's not particularly useful for anything at the moment, but it's very exciting to think about.
When you say discovered, are these scientists simply doing trial and error in a lab somewhere, or does someone have an inkling that these might exist, we just need to figure out how to do them?
So we know that they should exist. In theory, any number element could exist. So before the most recent four that were discovered, so 118, 117, 116, 115, we used to have a periodic table and it had blank spaces in them. So we know that there are supposed to be, the table is a very specific shape, it's a diagram, and there are blanks in it, and we know what's supposed to go into those blanks. So people were out there looking for these elements and figuring out. So the big ones you can make by basically smushing other atoms together. But as I said, they're not very stable. But yeah, we knew that they should exist. And we had these gaps in the table. Now, the table, the way that we draw it at the moment, is basically full now. But that doesn't mean that element 119, 120 doesn't exist at all. But we might actually have to redraw the table in order to accommodate those new elements if we do discover them.
We know quite a lot about the most common elements we find in the universe, things like hydrogen. What about the rare ones, though, Elisabeth? Can you tell us a bit more about the things that are quite hard to come by?
Yes. So of all the elements in the periodic table, there are 11 or 12 that we think we could actually run out of in the next 100 years. So that means we dig them out of the ground, we mine them, and then we use them in stuff. And if we don't recycle that stuff, then we're not really going to have these elements to use anymore. So a good example are the elements that we use to make up our mobile phones, so our smartphones. So you probably don't know this, but if you have a smartphone, it contains 30 different naturally occurring elements at least, and 6 of those we think they could run out within the next 100 years. So one of them, you might not have heard of this element, but it's called indium. And every time you touch a touch screen on a phone or a laptop, you're touching indium. So indium is used to make a compound, so that's a kind of collection of lots of elements put together called indium tin oxide. And this compound is very unique. It conducts electricity, it sticks to glass, and it's transparent, which means it's perfect for using touchscreens. But indium is one of the rarest elements on the planet. It exists in the ground, but it's in very, very tiny quantities. So it's a byproduct of zinc mining. So when we mine for this other element called zinc, mixed in with the zinc are these tiny amounts of indium. But in order to get a few milligrams of indium, you need to mine a whole kilogram of zinc. And then you have to separate it out. So it's very hard to get hold of, and every single mobile phone has indium in it.
Why can't we simply make more of it?
So the conditions that are needed to make these types of elements are very extreme. So hydrogen and helium, for example, are made in the sun. And that's because it's very, very, very hot and it's very, very high pressure. And then all of the metals are made in stars or when a star dies and you get a supernova. So it's these very extreme conditions of high heat and high pressure that basically push atoms together to make bigger atoms. And we just can't recreate those conditions in a laboratory.
It's another reason why it's so important to recycle. Elisabeth, thank you so much for coming on the show and telling us loads more about elements.
You're very welcome. It was great talking to you, Dan.
Kareena's Chemistry, with support from the Royal Society of Chemistry.
Super smug Sasha with the perfect flicky hair got a diamond ring for her birthday. It's so pretty. Oh, I'd love a diamond. Hey, I wonder if chemistry could make one for me. A really twinkly one. Now that would be cool chemistry. No chance, mate. I might be a chemistry superhero, but it can take thousands of years to make natural diamonds, and I've got plans for later. Anyway, if you want amazing crystals, there's plenty here in your house already.
Where? They're definitely not in my jewellery box.
Nah, not there. Downstairs in the kitchen. It's salt.
No way is salt going to be as cool as diamonds. No way.
Wait till you see. Salt isn't just a cool crystal. It has a load of superpowers too. Let's get tiny and check it out. You have a salt shaker, right?
Oh, salt crystals. They're well pretty. They look like squares, or more like hundreds of tiny white cubes. I can see right through them. They are like tiny diamonds.
They're pretty, aren't they? Crystals are a solid, where the atoms and molecules are arranged in a repeating pattern. Diamonds are okay, I suppose, but salt is just incredible.
Incredibly tasty, maybe. Salty chips. Salt and vinegar crisps.
That's because of the sodium. It's the main element in salt. Sodium is one of the chemicals our bodies need to survive. That's part of the reason salty things can taste good to us, and why people in pretty much any part of the world like putting salt in their food. Ooh, I could really fancy some chips now.
They are pretty, but they don't really look like superheroes.
Okay. One of salt's superpowers is what happens when you put it in water. Cue the water!
Oh no! The crystals are disappearing. Is that their magic power? The amazing disappearing salt crystals.
If you tasted the water, you'd know the salt hadn't disappeared. The crystals are dissolving in the water, and if there was a prize for being the best thing ever at dissolving, salt would be it. Let's get down with the molecules to see what's happening.
It looks like the salt molecules are being ripped apart.
That's right. The two sides of the salt molecule are like total opposites. One has a positive charge and one has a negative charge. This makes them want to grab onto other molecules.
What, like to get away from each other? Me and Misha are like total opposites, and sometimes I need a break from her too.
Kind of. Water is the same in a way, and as the water and salt molecules grab hands, the salt molecule is torn apart, And that's how dissolving works.
There's a lot of it going on. Hardly any salt molecules left.
Yeah, water molecules just can't help themselves. They don't just swish about waiting for the salt. They'll even travel towards places where things like salt are taking up space.
Hey, it's a bit like the heat energy we saw in the fridge and the chemical energy in the battery. The water wants to share itself about too, doesn't it?
Yeah, chemistry is full of stuff sharing itself about, and water and salt together make a powerful double act. The water will even run through cell membranes of living things to get to where there's less water in a solution. Look, there's some cells over there in the salty water. You can see what I mean.
It looks like the cell is collapsing. It's deflating like a balloon.
Yeah? The water has travelled from an area of its high concentration, inside the cell walls, to an area where the concentration is lower, because of all the salt. Can you see what it's done to the cell?
Looks a bit limp and floppy now, all empty. Poor cell.
Ah, don't be sad. The clever bit for us humans is that germs can't grow where there's not much water. So food cured with salt lasts longer.
Because the water travelled out of the cells. Hey! Is that why Dad washes grazes with salty water? It kind of deflates the germs.
Yep. Salt is great for keeping cuts clean, as well as preserving food and being tasty on your food. I told you it had superpowers.
We even put salt on the path when it's snowy.
Yep, another superpower. Salt and water together are harder to freeze, so it melts the snow and ice.
Kareena!
That's Dad, I gotta go. I think it's fish and chips for tea.
And come on, you'd rather have salt on them chips than diamonds, wouldn't you?
Definitely. Even super smug Sasha would have to agree with that. Bye for now.
Kareena's Chemistry, with support from the Royal Society of Chemistry. Find out more at funkidslive.com.
And that is it for this week's chemistry special of our Fun Kids Science Weekly. If you want to find out more about the International Year of the Periodic Table, there are amazing resources on the Royal Society of Chemistry's website. Head to rsc.org/IYPT. You can learn loads more about the periodic table and all the elements that are inside it. If you've got a science question that you want answered on the show, you need to leave it for us as a review for the Science Weekly over on the Apple Podcast Store. There's a little comment box at the bottom. That's where you stick your question. Also, leave your name and 5 stars so I know who to say hello to. While you're on there, it's a brilliant place that you can hear all of the science series. You've heard a few today. Loads more that you can keep busy with. They're also on wherever you get your podcasts from, really. Spotify, Google Podcast, places like that. They're on the free Fun Kids app and at funkidslive.com. And Fun Kids are a children's radio station from the UK. You can hear us all around the country on your DAB digital radio, on that free Fun Kids app, and at funkidslive.com.